I took these notes myself from the reading, okay? If you already got them, you're in good shape. So, random variable. Talk about a random variable. Random variable is the numeric value that's based on the outcome of a random event. And a lot of times you'll see a capital X to denote the random variable.
What's denote?
Represent. Yep. Usually a large X is used to represent that random variable. And they'll use a lowercase x to represent a specific outcome of one of those within that random variable. Okay. Represents a specific outcome that X could have. So in the situation that I gave you, X, whether I'm looking at it from my perspective or your perspective, okay, we'll call it your perspective. Based on the situation that I gave you, which was this one right here. Here's your game, so I got it on video here. Pay $5 to roll a dice. Here's what could happen, right? Okay. X, we're going to say X denotes the random variable. So I would say X would represent your winnings, or how much money you get, or your change in money, if you will. Okay? So large X in that case is money won or lost. Okay? So going back to the example we did, 'cause I'm trying to relate this to a real life situation here. The big X is going to represent the money you win or lose. Okay. Now, what were all the possible outcomes? So in other words, what could little x potentially be for you in your case?
Plus 10, plus 5.
Plus 10, because if you pay $5 to play the game and you roll a 2, you've actually just gained $10, right? So Drew says we could have x is 10. What else?
Plus 5. Or, yeah, 5.
Because if you win the $10 prize, you've actually just gained $5, right?
X equals -3.
X equals -3. And x equals -5. So I'm trying to show you how the notation could potentially be used here, okay? The big X just kind of represents what your variables are going to be, and then the little x's represent the actual outcomes that could happen from whatever we're doing. So in our case, in this little gambling game, okay, X represents your money won or lost, and these represent possible outcomes of a particular, of something within that X. Of all the things that you could win or lose. Is that making sense? These are all the possible outcomes within big X. Is that all right? Okay? I'll come back to this page. you will be drawing a probability model. Probability model. And that is a collection of all the possible values of x and their probabilities. So it's basically going to be a table. You'll probably make a table. And it's going to be a collection of all the possible values of x and the probabilities that go with them. I got this? No? Okay. Thank you. So we're just going to kind of organize our information. All right? These are going to be, we'll do it in a table. A lot of times you'll see this, and then you'll see this as your two columns, all right? So these are just all the x values within big X, okay? But here's all the key stuff that we're after. X equals 10. What is the probability of x happening? What is the probability of you winning $10? 1 out of 6, right? Because you had to roll a 2 to win $10, correct? And the probability you roll a 2 would be 1/6. How about the probability you win $5? It was also just one way, so 1/6. Probability you lose $3?
1/3.
1/3, because there was two ways to do that, so 2 out of 6, or 1/3. And the probability you lose $5.
1/6.
Still 1/3, isn't it?
Yeah. Oh, I didn't see that.
Hard to believe that it never happened to any of you guys.
We're just good rollers.
I know. You called it.
Pretty
You
sure the
said
dice was weighted actually.
yeah. Should have picked different numbers to represent winners.
The house.
This is your probability model. That's an example of a probability model. It's a collection of all the possible outcomes. So that's what this top row is, all the possible outcomes, along with all of their probabilities of occurring. What you're going to find next is going to help you determine whether or not it was a smart game to play or not. Okay? You are going to be finding the expected value also called the mean of a random variable. Okay? You're going to be finding the expected value, or on average, what should happen. On average, what should the outcome be? Okay? And the way you do that, here's kind of the, so remember that represents mean, right? Mu. That's going to be our expected value, so E of x. And And the way you will find that is you will add up, remember that's the sum notation, summation, this is sigma, yep. You'll add up all of the x's multiplied by their probabilities. Again, this is sigma notation, meaning you're going to add together all of the x values and their multiplied by their probabilities. So you're going to add up all those products.
So what do all the number, or what does the mu and the e of x represent?
They just, when you see this, I want you to understand that means find the expected value. So this is the notation you'll see. Find the expected value. It means the same thing as the mean, but you'll see e of x for the most part. Okay, but I wanted to put it with this because so you remembered it. It's the mean or the average of what should happen in a given event. Does that make sense?
Yeah.
And then how do you find your expected value? This is what you do right here. Okay. So in our example, my expected outcome or my expected value would be, okay, I got to take all those outcomes and multiply it by their probabilities. So one of the outcomes was you winning $10. What was its probability? 1/6. Okay? So in other words, I'm going to take 10 times 1/6. Because I'm taking its expected outcome times the probability of it happening. Plus, I got to do it for the next one. Another outcome was getting was winning $5, and the probability of that happening was also 1/6. -3 times 1/3. And -5 times 1/3. Does everybody see that I'm taking an outcome times its probability, outcome times its probability, outcome probability, outcome probability, and I'm going to add them all together. Everybody see how I'm using that rule? Okay? I'm going to probably need a little bit of help here.
I got some things.
Yeah, I'd be better off going 10/6. If you guys want to do this on the calculator, that'd be great. 5/6. -1. -5/3. So 15/6 minus, that would be -9/6. Did you get -1/6 or negative?
Yeah.
So decimal would be what?
No.
Negative point what?
1/6.
So is that plus -5/3 there?
Yes, plus -5/3.
So is that saying we should have lost money?
That's saying, yep, on average, but is it a lot of money? Not 16, 17 cents, right? So, was $5 probably a fair amount to get people to play this game? I would say so. I mean, yeah, you're still going to lose on average, but you're not losing much. Like I said, I just made this problem up, so I had no idea what this expected value was going to be. But now if I asked you, what would be your expected value of playing this game? On average, over millions and millions and millions and billions of trials, we would guess that your expected outcome would be losing about 17 cents every time you do it.
Could you leave it as -1/6, or does it need to be that?
Yeah, no, I
didn't know if you were circling.
yeah. No, just because I know a lot of people did it on a calculator, I left it as that. I mean, I'd accept either answer, Drew. It really doesn't matter. Okay. Now, So my expected outcomes was losing 16 cents. Obviously, had I changed the price to, okay, it's going to cost you $7 to play this game, then we would have had some differences, right? Because then this would have just been 8, this would have been 3, this would have been -5, and -7. And that would have definitely had a big impact when you found the expected value, and you would have noticed that on average you would be losing. Probably over $2.
How many times is it saying like that we're gonna be doing that to lose 16 cents?
But that's just saying on average that's how much you would lose each time.
Oh,
On average. Now is it possible to lose 16 cents each time?
no.
No, because there's those outcomes. That's not a part of the outcome, okay? But what they're saying is on average, the people who play the game are losing 17 cents every time they play the game. So, theoretically, because it is completely random, if I would have you guys play this 1,000 times, okay, I would guess I would be close to being up $170. Did I do the math right? 17 cents times 1,000. You gotta move it 3.
It'd be like 166.
Yeah, I mean, yes, I was rounding that to 17, but yes, absolutely. So I would guess that if somebody played this game 1,000 times, theoretically I would be up $166. Okay? Does it mean that that's going to happen? No. But if you think about it, casinos essentially make their money doing this. Okay? When people play slot machines, yeah, you win every once in a while. But they have all the probabilities of certain winnings calculated so that every time a person pushes a button on a slot machine, on average, over millions and millions and millions of spins, the casino's getting a certain chunk of that. Hence they stay in business as long as they got people pushing buttons. Because it's calculated over millions of times that it's going to, every time you push a button, the casino is going to average a certain amount of income. You just got to hope you're pushing the buttons at the right time when it actually hits for you. It's complete luck. So, kind of an interesting topic. That's expected value. What questions do you have on finding expected value? It's really pretty easy. Make your probability table like we did, and then add all of the outcomes times their probability together to get your expected value. Okay, Drew?
If you change the price to pay to 7, would it go down? Or?
Yeah. Yep. What we would have seen, what I did. If I would have changed it to 7, okay, this would have just been 8, 3, -5, -7, right? So 8, 3, -5, -7. So 8/6, 3/6, that gets me to 11/6. -5/3, -7/3, so that's -12/3, which actually means -24/6. So 11 minus 24, that'd be -13/6. So it's exactly corresponding. That's now -2 1/6 instead of -1/6, which makes sense because now you're paying $2 more every time. But I'm showing you how mathematically it still works out to be exactly that. So then I would say on average, you would have lost over $2 each time you played the game when you paid $7. So $5 was actually close to a fair price, but I'm still going to probably win out in the end, even though on your small sample space of, what, 8, 9, I ended up down $10. But I bet if we keep going, I'll probably end up a little bit on top. But $5 was close to fair. It would get people to play. So that's expected value. You probably took notes on standard deviation, things like that. I'm not quite there. I want you to get this expected value down first. So assignment for that. Page 383, 1, 2, 15A, 16A, 3, and 5.